Let's see. Okay, we got 12. There'll be a few more coming. If you want to turn on your cameras, it may help me. Just, I mean, if I can see you, it's a little easier for me to understand if you're getting it or not. Getting to the end of this. $16, $17, $18. It's 17, went down to 16, that's all. Okay, does anybody have any comments, questions while we're waiting for everybody? Can you all hear me?
Mm-hmm. Yep.
Yep.
Can hear
I can hear.
My appeal to turn on your cameras, it's not working. It doesn't matter what you look like. I just want to make sure that I can at least get a read on your faces. Lydia's the only one that's got a camera on right now.
Dr.
There's somebody.
Baginski,
Thank
I'm
you.
eating breakfast. I will turn it on as soon as I'm done eating.
You can eat breakfast. It doesn't bother me. It doesn't matter. I mean, the other class, guys who got long beards, hairs, they don't care that I have. Anyway, so first thing, anybody have any questions at all? Nothing? Okay. Let me do one thing. I'm going to cast the screen here in a second.
Actually, do have a question. Could you work 7.37, the 7.35?
Yeah, I'll be happy to. I'll be happy to. Let me go ahead and get this camera. First, I got to cast this. And then you should be seeing a screen. And then I'm going to get my camera up. Hopefully it'll work. Oops, that's not my camera. There it is. All right. What the heck? I was playing with some of these optional things on here. 7 point, which one was it again?
The 7.37. You have a note on there saying this is 7.37 while it's labeled 7.35. The yn equals 0.5xn plus 0.29 parentheses xn plus 1.
This one you want, or this one? This one, right?
Yes. The first one, yes.
Wait, 3.5 or 3.7?
3.7.
Okay.
The one your finger is on.
Thank you. All right, for this one, it says y of n is equal to 0.5 times x of n. And then it's plus, oh, this is one of those, it's going to go on forever. 0.29 x of n plus 1 plus x of, or plus, what is that? X of n minus 1. And then plus, minus, geez. And this has got a grouping, right, of x of n plus 3 plus x of n minus 3, okay? And then, oh my goodness, plus 0.005 x of n plus 5 plus x of n minus 5. This smells of cosines all over the place. And that's the difference equation. Compute the expression for h of omega. Express it as a sum of 3 cosines. Yeah. Okay. For this one, this is supposed to have, I'm sorry, I'm going to put this here. I didn't get that right. This is plus x of n minus 1 here, right? Y'all see that? Sorry. What I've done is just restate the problem right here. You have your books. This is 7.37. You see it, everybody? Okay, if you can see that. Now, the thing about this is you don't have to do it this order. I'm going to do a z transform, and then I'm going to put in z as e to the j omega for the frequency response, because that's what it's asking. So if I do this, then I would get y of z here, right, is equal to 1/2, and it would be x of z, right? Y'all see it? And it's going to be plus what? Plus 0.29, and then it would be x of, and what's this going to be? This is x of z. If it would be n minus 1, it would be divided by z, right? If it's n plus 1, it's multiplied by z, isn't it, class?
Yes.
Let me tell you where it is in the tables. There is no x of 0. This is on this is on page 370, and it's 4. And so it's going to be z times x of z, and it's going to be plus x of z over z, or just times z to the minus 1. That's fine. All right, then the next one here, cross that off right there. This one is just going to be minus 0.042, and then it's going to be times z cubed times x of z plus z to the minus 3 x of z. And finally, you're going to have this one, which is plus 0.005. I think you're going to see this in a second. That's going to be z to the 5, right? X of z plus z to the minus 5 x of z here. You all see what I've done here? I've just taken the z transform and I've assumed no initial conditions, correct? Okay, now after I have that, since they want the frequency domain response, initial conditions don't even appear. You don't even care about them. The next thing I do is just let z equal to e to the j omega, because that's going to be the frequency domain response, right? And we assume the input, we're going to assume, since we want a frequency domain response, we want h of omega, right? And that means x of n would be equal to delta of n, which would give me 1 in the frequency domain, the z transform of that. Do you agree with me, everybody? Since we want h of omega, that means the input would be h of omega in the time domain is h of n. And when you want a frequency domain response, you would assume an impulse, bless you, an impulse, the input would be an impulse. So basically all these values of x of z become 1. That's what I'm really saying. X of z then becomes 1. Do you agree with me, everybody? You can do this. You could take the ratio of y over x, and that's just as well. You could say h of z was equal to y of z over x of z. That's the definition. but I'm going to cut to the chase. I'm just going to let this be h of z goes to e to the j omega. Now, when that's the case, then I come down here and I say, just looking in this at this here, that means I have h of omega. The first one right there, there is no z, so it's just 1/2. Do you agree with me there? The coefficient of, remember, x of z becomes 1, correct? So it's just 1/2. You see this, Ashley? What I'm doing? All right. Now here I have plus 0.29, and now I have e to the j omega, right? Plus e to the minus j omega. I'm writing it down term by term. The next one is going to be minus 0.042. That's this. And it's going to be e to the j 3 omega plus e to the minus j 3 omega. And then the last one here becomes plus 0.005. And this is e to the j 5 omega plus e to the minus j 5 omega. Does everybody agree with that? Close?
Yes.
Oh, I gotta admit, there's somebody waiting.
I got it.
Okay, good. Hold on. I'm trying to move something over here.
You know the gold necklaces I'm talking
I couldn't understand you. What? Could you say that again? Okay. If there's anything on chat or anything, let me know, because I'm going to be looking down here. Now, y'all see that this, I mean, cosine of omega is just equal to e to the j omega plus e to the minus j omega over 2, correct? Everybody? So if I multiply by 2, then I have this. Now you'll notice that's this right here. This would be 2 times cosine of 3 omega, and this is 2 times cosine of 5 omega. Do you see that? Okay. So this h of omega, this is kind of an interesting one, is 1/2 plus 2 times 0.29 times cosine of omega minus 2 times 0.042 times cosine of 3 omega. And then the last part is plus 2 times 0.005 times cosine of 5 omega. Do you agree with me? Now, if we want to plot that, we can do it in math. Does he ask for plotting it? All right, we expressed it as a sum, and then plot at, so he wants a plot of this basically for a range. He just tells you what the increment should be, but we can plot it for a lot more points than that. So if you wanted to plot it, what I would do is this. I would just go ahead and get MATLAB. Let me open another tab here. Y'all can see MATLAB, right?
Yes.
People?
Yep.
And if I was going to do this, with all my codes, it's always clear all, close all, and CLC. That just clears the command window down here at the bottom. And then I'm going to type in my omega value. So I'm just going to call it small w. It's like capital W. And it'll be a linear spacing. Linearly spaces points. And I'm going to go from minus pi to pi. So the range is from minus pi to pi. And the next value you put in here, I'm going to leave it to be n. That's the number of points you want. So I'm going to have n equal to like 400. It can be anything. Usually it's 2 to the n points I put down, but I'm going to just put 400 for now. Now I put in the function I want to plot, so I'm going to call it y is equal to, and it starts out with 1/2, right? So 0.5 times, or 0.5, sorry, plus, what is it, 2 times 0.29 right? Times cosine of omega. Tell me if I missed anything. Then it's what?
Minus 0.084 cosine 3 omega,
Point,
or 2 times 0.042.
all right, 0.084, right?
Yes.
Times cosine of 3 omega. And then plus
Plus
0.0
0.01
times
cosine
cosine.
5 omega.
Now, plot. I'm going to say one thing. This one looks like it's. I'm not sure you're going to see a lot of contrast, a lot of resolution, but we'll take a look at it. Now I'm going to plot this. Just plot omega, comma, and then y, just to get an idea of what it looks like. We can title it later. Let's just take a look. Oops, sorry, it's 7. What? Do a grid on here. It's a low pass filter, that's for sure. You can see the 0.5. It's really kind of, well, I'm not seeing a whole lot of anything except that these coefficients were probably chosen to get rid of the ripple. Okay, can you all see what's going on there? You all see the plot, right?
Yes.
I got somebody in chat. Hold on. For the last two did he forget to multiply by 2? No, you guys multiplied by 2 and gave me the coefficients. What happens, I believe, right?
Mm-hmm.
Okay. So that's the plot, and I'm going to make a comment here. When I look at this plot, there's no ripple. Now, this is something I showed you before. Let me see if I have it. I had a website that I talked about here. Did anybody look at this website? We're going to talk about this. I'm going to pull it up and show you something. Let me shut that down. But this is kind of cool. There's a lot of stuff on the internet. Now, when you're talking about in the frequency domain and you're talking about a filter response, you all see if this is omega going up here. I don't know how I can make this screen. This is kind of neat. I can literally do this just by touching this. But what it really does is this. It's saying if you have a frequency, you're looking for a filter response like this. Okay, and I'm going to go through this. This would be the impulse response. This is non-causal. So this would be something for us to do any kind of filtering with this. It would have to be a FIR filter that I mentioned briefly, didn't I? FIR filters or not? You all realize this is non-causal, right? You got me on that? And did I mention FIR filters or not here?
You might have. It would have
Finite
been
impulse
very
response.
briefly.
All right, we'll talk about this, but I'm going to show you this right now. If you just have a rectangular window, it means you would literally have a filter where you're assuming that this would be almost square. It can't be square though. Then you would get this as the impulse response. Now, if you look at the order, if you want, the higher the order of the filter that I'll get into, the more suppressed are all these side lobes. And then this would be the impulse response. Now that's just a rectangular filter, but just trust me, these things are going to pop up. Now if you do something, and I mentioned windowing before, correct?
Mhm.
Now,
Yeah, you did.
a Hamming window, you'll see it suppresses all those upper frequencies. You still have a non-causal system response, but there's ways of dealing with that. That's a Hamming window. This is a Hanning, very similar, but you'll notice these side lobes are completely gone. Then there's a lot of things you can do with this. This is sort of something, once we talk a little bit more about filters, you're going to see that's about as close as you can get to an ideal filter right here. An ideal filter. We'll be talking about this. I wanted to make that applet available to you. So back to this. That's the filter response for the problem. Before I get into the filtering and stuff like this, any questions, any other questions about the problems? They were just basically taking a difference equation and turning it into an h of z, right? And then get somebody's wait. Then after that, plotting it, getting an idea of what it looks like. Y'all with me on this?
Could you do 7.36?
Yeah. Sure. Let me get the camera. Now y'all have the solutions, right? The answers, the solutions. Didn't I post both, class?
Yes, we do. Mhm.
For 7.36, you have two frequencies. You have x of n equal to, what is it, cosine of 2/3 pi n, right? Plus cosine of pi over 2n. So this would be like one frequency. That would be, call it omega naught. And this would be like omega 1. There's two frequencies you're talking about. And then they give you a difference equation. They want you to figure out what A and B would cause the output y of n to be just a sine of pi over 2. So for his difference equation, I'm going to go first, I'll write down his difference equation. He has y of n plus ay of n minus 1 is equal to x of n plus bx of n minus 1 plus x of n minus 2. Everybody probably see this in their books. Do you agree with that? Who asked this question, by the way?
I did.
I can't see.
Okay.
Who?
Shouldn't there be a y of n minus 2 on the left side as well?
Is there?
I'm not seeing one for
No.
36.
Oh, never mind. I'm looking at the wrong problem. I was looking at 35. You're right.
All right. I normally do the Z transform. I do this just routinely. So if you do the Z transform of this, we get y of z, and that's 1 minus a, right? Z minus 1. Do you agree with me, everyone?
Mm-hmm.
Over on this side, we have x of z, and then we have 1, right? Plus b z to the minus 1, right? Plus z to the minus 2.
I think it's 1 plus a z to the minus 1.
Wait. What are we looking at? Oh,
On the
yes,
left side.
yes. Thank you. You're right. You're absolutely right. These are all pluses, right?
Yes, they are.
Okay. If we're convinced that now, what I'm first going to do, and just bear with me, I'm just going to multiply by z, and here's why. I can see right here, I got a z to the minus 2. I would like a z to the minus 1 and a z to the minus, or I mean a z to the 1 and a z to the minus 1 here. for a lot of reasons. So I'm going to multiply both sides by, well, first I'll get h of z. I'm going to get h of z is equal to 1 plus b to the z minus 1 plus z minus 2 over, that's a plus, over 1 plus a z minus 1. Agreed? Now I take that and I multiply top and bottom by z, h, just z by itself. So now I have h of z, that's a legal operation, is z plus b plus z to the minus 1 over z plus a z, or I'm sorry, plus a, pardon me, just plus a. Agreed?
Mhm.
And now I make this comment. Leave that right there. What he wants is, he wants you to find a and b such that y of n will be equal to sine of pi over 2n, right? Is everybody with me on this?
Hmm.
All right, you see this frequency is what? That frequency is pi over 2, right?
Yes.
Now, what that means is he wants us to get rid of this entirely because that's a different frequency, right? He only wants to maintain this. Let me cut to the chase on this one because I think I'm spending too much time with the Z transform. Here's what we're up to. Remember, if you have anything at a constant frequency, either a sine of omega naught n or a cosine of omega naught n, and you put it into a filter, and the filter has some h of omega, your output in the time domain, and I've put this down before, y of n will be equal to the input signal times its magnitude. If you want to put an a there, you can. So it would be a right there. Then it would be the magnitude of the filter at omega naught, right? Then it's going to be either a sine or cosine. I'll take the sine in this case. The sine of, in this case, it would be omega naught n plus, there's no angle there, and just the phase angle of the filter. Agreed? All right. Now, you know that this filter that I'm showing you here, when I'll put it into the omega domain, h of omega would be equal to e to the j omega right here. And I'm going to put the second part right next to it. I mean, the last part, plus e to the minus j omega plus b, right, over e to the j omega plus a. Y'all agree with me there?
Mhm.
Now, this, I can go a couple of different ways, but I can say that's 2 times cosine of omega plus b over, and if I wanted to be clever, I could probably fool around with this and turn it into I can pull out an e to the j omega over 2, or e to the minus j omega over 2. No, e to the j omega over 2, and e to the j omega over 2 plus a e to the minus j omega over 2. But I'm going to leave that alone for now. And I have e to the j omega a. Now, one of the conditions is that h of 2/3
Isn't it plus
pi.
A?
It should be plus A.
Yeah, sorry. E to the 2/3 pi right there has to be equal to 0, correct?
Yeah.
Take a
Yeah.
look here. This frequency we want to get rid of in the output, so it has to be 0. Well, what would make that 0? Right? Well, one would be if 2/3 pi, if you just think about this, I would need this to be 0, correct?
Mm-hmm.
Y'all see that, class?
Mhm.
Mm-hmm.
Let me just see if I can spread this out so I can see better. Give me 1 second. I can't seem to spread this out for some reason. Getting a little better. All right, much better. Okay. Well, if I have this, remember the frequency is 2/3 pi. So if I have,
Slide it up
Two.
some, please.
yeah, if I have 2 times, let me get another page. H of omega was equal to, that was 2 cosine of omega plus b, right, over e to the j omega plus a. Isn't that right?
Yes.
Yes.
Right.
Now, when I take a look at the filter, when omega is equal to 2/3 pi, we want it to be 0. That implies that the numerator is going to be 0. So
Yes.
that means 2 times cosine of 2/3 pi plus b equals 0, or b is equal to minus 2 cosine of 2/3 pi, right? And if I think about that, pi over 3 is 60 degrees, correct?
Mhm.
2/3 pi is going to be 120 degrees, right?
Mm-hmm.
So the cosine of 60 degrees is going to be 0.5, correct?
Mhm.
The cosine of 120 would be minus 0.5, correct?
Yep.
And that means this would be equal to 2 over 2 with a minus or minus 1 would be B. Do you agree with me? Who asked?
Wouldn't it be
Be positive.
positive 1 because cosine of 2/3 pi is equal to negative?
Actually, you're right. It's 1. That was my mistake. You're right. So now I'm going to have a filter with h of omega equal to 2 cosine of omega plus 1 over e to the j omega plus a, correct? Now, if you take a look at this, and I take the 2 out in front, I would have cosine of omega plus 1/2, right? Do you all agree with me? I mean, I'm fooling around with a half angle formula here in a second, but let me see if I can find what I'm looking for here. Give me 1 second. So cosine squared theta is equal to 1/2 plus cosine 2 theta over 2 . That's not going to do what I want. All right, we'll do it a different way. If we have, okay, if we have this functional form here, and I'm going to write it down again, equals 2 cosine of omega plus plus 1 over e to the j omega plus a that times the input was for that problem was a cosine of pi over 2n. So the input is x of n equals cosine of pi over 2n, and we want the output to be a sine pi over 2. That means y of n has to be equal to, the magnitude of that is 1, the magnitude of h of omega, and that means the magnitude of this has to be 1 here. At pi over 2. Now, what is it? At pi over 2, just look at this. If we want the magnitude of this to be the magnitude of h of omega to be equal to 1 at pi over 2, well, the cosine of pi over 2 is 0. Do you agree with me, everybody? All right, so this would go away at that frequency, and I'd have 1 over e to the j omega plus a, and that's actually 1 over, and the magnitude of that would, this would be e to the j pi over 2 plus a. And what is e to the j pi over 2? I better go down here. This would be h of omega equal pi over 2. That would be 1 over e to the j pi over 2 plus a. And that's going to be 1 over the magnitude of this. Well, really, what is that? Isn't that just j plus a? Class? Y'all agree with that? If I have e to the j pi over 2, that's j, right?
Mhm. Yeah.
And we got rid of the cosine up here, becomes 0 at pi over 2. Now, for this thing to have a magnitude of 1, a would be 0. Do you agree with me?
Mm-hmm.
And if a is 0, I want to just flip the page over. If a is 0, then our final form of the function looks like 2 cosine of omega plus 1 over e to the j omega, doesn't it? Isn't that the final form of h of omega? I don't know what he has down, but I'm just saying that's it, right? Okay, now if that's it, hang on for 1 second. If that's the final form of h, then y of n would be equal to the magnitude of the input. The input was, remember, the input was equal to simply cosine of pi over 2n. We got rid of the cosine of 3/2 or of 2/3 pi n, correct? Because the filter is 0 there, right? Everybody remember this? I'm sorry, I'm not trying to hasten everything, but I have to move a little faster. All right, now what's the output with this? So the output would be, first I got to evaluate this at pi over 2, and that's just 1 over e to the j. When I evaluate the filter at, let me do it here, h of pi over 2, that's going to be equal to 1 over e to the j pi over 2, or 1 over j, correct?
Mm-hmm.
Right. So that's really equal to h of pi over 2 is simply minus j, right? Everybody?
Mm-hmm.
I'm trying to, and what is that really? That's 1, or really e to the minus j pi over 2, isn't it? I could have gone right from here to here. Do you agree with me? What's the magnitude of
Yes.
that? Magnitude of that is 1, correct? The
Mm-hmm.
magnitude of h of pi over 2 is 1. So my output would be 1 times, then it's the cosine of the original frequency, pi over 2n, then the phase angle associated with the transfer function. And the phase angle is minus pi over 2, correct?
Mm-hmm.
I hope I'm not boring you too bad with this. But now, what is this? Well, isn't a cosine minus 90 degrees sine? So this is really equal to simply the sine of pi over 2n. And that's what he wanted you to prove. Who asked this again? I heard your voice, but I didn't see it light up the box.
Jacob Landing.
All right, Jacob, did that answer your question?
Yes, sir.
I don't know how he did it in a book. This is a little cumbersome problem because there's a couple things going on. It's just not one thing. You had to get a 0 at 2 pi or over 3, 2/3 pi at that frequency. And you had to also at the other frequency have a phase shift of minus 90 degrees. So that's where you balance the A and the B. Got it? That's not a bad problem though. All right, any other questions about the homework? I didn't give you much. Anything? Nothing? Okay. Last thing I'm going to tell you, in the book, in chapter 7, what it talks about right here, this is the discrete time Fourier series. Now, and this is the final part is the DTFT that we covered first before we did the Z transform, because it made sense to go from Fourier to discrete time Fourier first, and then to go to the Z transform. Laplace and Z are related, Fourier and DTFT are related. That's the way I try to keep that in your mind. I try to make the analogies. Now, the discrete time Fourier series is this, and I'm going to just mention this to give you perspective. I'm going to get to filtering, but oh my gosh, 5 minutes. Follow me on this. Remember before, if we had a periodic signal, say we had a signal like this, periodic signal like this, and this is in the time domain, that would be 0, that would be period t, had an amplitude of a, call this x of t. You all know that, right? It goes on forever, it's an everlasting signal. I made the case, and you know it, x of t can be given as a summation from n equals minus infinity to infinity of some c of n e to the j and omega naught t. Here, omega naught was equal to 2 pi over cap t, the period, right? And you all know how to get those coefficients, c of n. Remember, I showed you that c of n was equal to 1 over t, the integral from 0 to t of x of t times e to the j or minus j n omega naught t dt. I'm just putting it down to, you know, just trigger your memory. Now, this is a continuous time Fourier series with a representation that's exponential. What if we sampled this series? And what if we sampled this series? Now we would have an x of t, would have an x of s of t, which would be an infinite series of delta functions, t minus nts, right? From n equals minus infinity to infinity. And that's going to be multiplying the actual x of t. Do y'all remember how we created a sampled signal? We took the original signal and just multiplied it by an infinite series of delta functions, right? Now, this is a sampled series. It has only values at discrete points in time, nts. Now what happens when you have that? And I'm not going to have time to do the whole thing on this, but if we want to create the equivalent of this, what we'd end up doing is this. This right here would become x of n. It would not be t. it would be a series, a summation, right? But the summation in the book, he's going to have it. It's going to be a finite series, finite summation. And I'm trying to see where he does it. All right, in his book, I'll take you from here to here if I have time, but because I'm not going to have time to get to filtering right now. What he ends up doing is saying that, remember, this is the series, the continuous time series, right? That's what I just put down. Now he says if you sample it, then in fact what's going to happen is now your, first of all, your x of n, oh, that's the inverse. Yeah, here's the case. He's going to say that this thing's periodic. That means x of n equals x of n plus n naught, where n naught would be the fundamental period. And then he makes the case, if that's true, then I can get this expansion, where that's going to be equal to the frequency domain equivalent to C of n. Remember how we had or C of k? This is the frequency domain equivalent. You'll notice it's normalized by n naught. Remember before we divide by 1 over t, right? For continuous time, we had this 1 over t, right? Over here, our x of n is going to be represented, and this is going the inverse of it, so it's not actually. Let me do it this way. I'll just give you the frequency domain coefficients. X of k would be equal to 1 over n naught right there times the summation. And it's just going to be from n equals 0 to n naught minus 1. Here, n naught is equal to the period. I'll do this next time. And then it's going to be times x of n times e to the minus j omega naught n. And I should say this, omega naught is equal to 2 pi over n naught. Let me try to make sense of this to you, because I know I'm going fast and I don't want to lose anybody. Give me a few seconds here. This is the continuous time representation we're used to seeing. This is continuous time. X of t goes to actually C of n. Even though they're discrete values of n, it shows you that these coefficients represents the relative strength of the signal at each harmonic, right? N equals 1, it's at the first harmonic. N equals 2, it's the second harmonic, and so forth. Do y'all remember that class?
Mm-hmm.
Now, when you sample a signal like this, and I can't go through it from here, I don't have time, then you end up getting this, because you literally put this sampled signal right in here. When you put this sampled signal right into this equation, what ends up coming out is going to be this right here, where now instead of C of n, you have x of k, and you'll get this. I'll do that next time. I wanted to just touch on this today, and I'll ask you to do some reading and a few problems. But really what you're doing is, if you have a periodic signal, everlasting signal, and you sample that, you only need to take a finite number of data points, just like before we integrated only over a period. Here, you only have to sum over a finite number of data points to get the values of x of k. There's a few tricks I got to tell you about later. My time is up. Next time, I'm going to give you some reading assignment related to this, and I'll give you some problems with solutions. But I want to get to filtering and applications of what we've learned with Z-transforms next time. And I'll try to be a bit more prepared to move on quickly from homework. All right, but we're in good shape in this class because we're well ahead of, I think, the other class. I don't know if you've heard where they are, but I don't even know if they started Z-transforms yet. Does anybody know? But we're in good shape. Yeah.
I knew that they did Fourier. They started Fourier like a week ago.
Yeah, they're just getting through Fourier transforms. I have friends in the other class.
You mean discrete time Fourier transforms or Fourier transforms?
Just Fourier transforms.
Fourier transforms.
You guys are supposed to have Z transforms and applications through this course. Fourier were way back in the Stone Ages. So who's teaching that course anyway?
Ian's son.
Well, it's his first or second time he'll learn. Because this is important for all the other courses. When I teach radar, and we guys into getting to comm, and you're going to get into random signals and systems, all this stuff is crucial. It's like circuits is to every other course related to real parts with inductors, capacitors, and resistors, and in transistors. You couldn't do GoFu News course in digital, I don't believe, without circuits. Isn't that right?
I think so.
It would be pretty tough.
Yeah.
What?
I mean, I think you could do it, but it wouldn't be easy.
Well, you're not going to get through a lot of the other courses. EMC radar, electromagnetics 2, random signals and systems, communication, all that is based on the fact that you have a clear understanding of what I'm showing you through this course. And that's why I spent a lot of time really trying to show the linkage between Z and Laplace transforms, between DTFT and Fourier transforms, and really harping on convolution and how it's irritating. So don't do it if you don't have to. All right, I'll give you some more homework. I'm going to ask you to please do this homework next time. And I may have an assignment for Friday that I'm going to collect. I'm going to figure it out as we go. Okay?
Okay.
Any other questions?
Dr. Baginski, a quick question. So what happened to quiz 6?
Oh, you want to know the truth? That's when it was on paper, right?
Yes.
That's in my office at the university.
Okay.
And I think I'm going to go back to the grade sheet. I thought I scored it. I thought I entered the grades, but I'll double check on that. I haven't been there in a while. I have to go up today to pick up something, but thank you. Lydia, send me another email about what happened to quiz 6 so I don't forget.
Okay. And I know that for a lot of us, we have a Digitron test on Friday. So if
All
the
right.
homework could be made till Monday or next Wednesday, that would be fantastic.
That's fine. But
Yeah, I know a few of us have 2 tests, Power and Digitron, both Friday.
All right. I hear you, but please do the reading for this class and try a few problems.
Okay.
Just so we stay up. And I don't know what the other class is doing. Take care.
Thank you.
See you next. Bye-bye.